So we're going to finish up the Fourier series chapter today. If you remember last time, I sort of thought about trying to cram it into last class, but I extended it to today. Part of the reason for that is looking at the schedule, because I decided to cancel the second project. We definitely have a little bit more flexibility in our schedule in terms of like timing. And so I'm going to take my time a little bit over the next 3 to 5 class periods, just to fill up the semester. We've got a homework due next Thursday. I'll hand out one more homework assignment before then, and then we'll have the final exam. And those are the only grades left out there. Excuse me. I think that's all I wanted to say. Thoughts or questions about anything before we get started here? Just mention to you that tomorrow is the last day to drop courses, just so you know. I don't think anyone on this call should drop our class, but if there's another class you're thinking of bailing on, just be aware tomorrow's the last day to do that. Okay, so let's finish this stuff. This last section of chapter 5 is about the error associated with Fourier series. So we know that Fourier series can be used to approximate periodic functions. And then what we saw in the video last time is that the Fourier transform can be used to approximate non-periodic ones. But it turns out, so the title of this section is Approximation by Trigonometric Polynomials. Well, it turns out that this expression right here, which you should recognize as the Fourier series, is called a trigonometric polynomial, right? When you start plugging in n's into this, it turns into a polynomial-looking thing, except that there are trig functions. And what we're looking at here is we're looking at the nth partial sum, right? In other words, this summation, so there's an f sub n right here, and that n corresponds to this n, right? So all those n's are the same here, and the idea is that we're not summing to infinity anymore, right? Usually in the Fourier series, there's an infinity right there, and then you just take as many terms as necessary to sum up. We're now approximating just n of those terms, and that's called the nth partial sum. You might remember that from Calc 2, like when you're talking about series. And it says here the coefficients are the Fourier series coefficients. Well, it begs this question. Let's say we want to approximate some function f of x, and it has the above Fourier sum. What choices of the coefficients, so an, bn, and potentially a0, I don't know why a0 is not listed here, would make it so that our approximation is as close to f of x as possible? And so we already kind of know, just kind of based on what we've seen here, that this is what the coefficient should be, right? When we have a Fourier series, these are the coefficients. But what we're going to do right here is we are going to derive those coefficients, by looking at this partial sum. Now, we want the function we're approximating to be as close to the function, the approximation as possible, right? And so let's define the error. It's a very common thing to define. So the error, which is we're going to define with a capital E, that's going to be how close our partial sum is, Fn, to the function we are approximating. And so we know that when we want to show that two things, or we want to measure how close two things are to each other, we use a norm, right? And specifically the 2 norm is commonly what we use. And so we know from previous sections that we would subtract the function minus the nth approximation inside a norm. Right, like we had introduced this concept when we were talking about vectors, like measuring how close vectors are from each other, but it also applies in situations with functions. And we have definitions for how to do inner products of functions, so we can do that. This is kind of similar to a homework problem, though. Sometimes it's actually easier just to square the right-hand or the left-hand side, though, or both sides, because if you remember, this ends up under a square root, right? You do the inner product under a square root, and so if you square it, it just gets rid of the inner product. And so we're really going to be thinking about this expression, the squared version of the norm, which is just the inner product of that thing with itself, right? So e squared from the inner product section is the inner product of the function minus the approximation with itself. Just going to pause there right quick. I'm going to let my dog in real quick. Give me 1 sec. Okay. So we want this to be as small as possible, right? This is the error. So you can think of, you can see we're subtracting the two functions, right? And so it's measuring how close the two functions are to each other. And so we want that to be as small as possible. And so we're going to minimize that, which is going to involve derivatives. But before we minimize it, let's go ahead and fill out this expression, because we have an expression for f sub n, right? It's the thing right at the top of the page here. F sub n is this Fourier series expression. And so I'm going to write the next step that we get after you plug in f sub n and you distribute some things within the inner product. So let me write that down. I'm going to kind of skip a few steps here, but let me know if this looks okay. So this is going to equal the inner product of the function with itself. But then we get a bunch of other terms. We also get, after you plug it in, after you plug in fn and then you dot it with the function, it looks like this. It looks like 2 f of x a0 plus the sum an f of x cosine nx plus bn f of x sine nx. So that's the second term. That's sort of like what you get when you plug in fn and then you distribute the fn with the f. That's this expression, right? You get like the f with all the coefficients. You get the f with the a0, the f with the an, and the f with the bn. And these are obviously the parts of those terms. And then there's a third term that you get when you consider these two functions being dotted, the fn dotted with fn. That one ends up being even more complicated looking because you have two infinite sums dotting each other in some sense. And so that ends up looking like this. It's a very big, long, complicated looking expression that looks like this. Again, this is just the expression that we would obtain after we substitute in the formula for fn, so the formula at the top of the page, and then we distribute through the two different inner products. The last term is a double sum, so this one is k equals 1 to n equals 1 to n of an bk sine cosine. Running out of room. I'm just going to pause there a second and just say again what we just did there. I wrote down the expression for the error, which is which is the norm of the difference between the function and the approximation. We know that that's an inner product thing, so I wrote down the definition of a norm. And then I substituted in the expression for fn, which is 3 separate terms, including an infinite sum, right? And so I plugged that into each one of those places and then tried to simplify this down together. And so like the f's multiply each other to give you this one. The f and the fn's multiply each other to give you the second line. And then when the fn's multiply together, it gives you the third line, which is particularly complicated because you have two sums. That's why this one at the end ends up being a double sum, because you have like two sums that are multiplying each other. And I understand if this is like, whoa, where the hell did this come from? But I hope you at least see what I'm saying in terms of like plugging in fn and expanding it, and maybe you could at least just take my word for it that this is the expression you get. There's a little bit more detail maybe in the textbook, but not too much more. Can I answer a question about that before we keep going? It's not like end all be all if you understand that or not, but if there's something on your mind, I'd be happy to talk about it.
So you end up getting a bunch of smaller inner products, or are those just parentheses?
Yeah, those are all inner products. That's right.
Okay.
So each one of these things are inner products. Basically, like when you do this inner product, you end up having like two subtractions, two differences that end up multiplying in some sense. And so when you distribute, quote unquote, it ends up looking like this. It's distributing in the inner product sense, though, not in the parenthesis sense. Other thoughts? And so the question is to remind you what we're trying to do. We're trying to figure out what A0, AN, or BN need to be in order to make this as small as possible. And so to minimize error, anytime you see the word like minimize or maximize or something like that, you should be thinking about calculus. Because if we want to minimize error, we want to find the min of this expression, right? Minimize that. And so we're going to take a derivative with respect to one of the coefficients. So with respect to one of either A0, AN, or BN, set it equal to 0, because that's how you find minimums, right? You find the critical points and solve for either A0, AN, or BN, depending on which one we're messing around with. So I'm just going to show you one of them and show you sort of the easier one, just so, because I think it's a little bit easier to see what's going on there, to show you that we actually do get the expression for A0. So I'm going to show you that when we take the derivative with respect to A0, we end up getting this expression for A0, which is what we've been using this entire time. But now it's just time to sort of show you why and then apply this a little bit. So let's do it. So the one we're going to do, again, is kind of the easier one. Let's take the derivative with respect to A0. And so we're going to take the derivative of the error expression we have with respect to A0. And so this is going to tell us how the error changes as A0 changes. And when you solve it equal to 0, you find the value of A0 that minimizes it. That's the process we're about to follow. We're going to do that on the next page. So let's look at this before I flip the page. We're going to take the derivative of this big long expression with respect to A0. So if there isn't an A0 in there, this is like a partial derivative for those of you who have taken. Maybe you do this in differential equations, not really sure, but the partial derivative like you would do in Calc 3, for example, right? And so you think about the x's as being constants, and you just take the derivative with respect to A0. So like, for example, this first term, this inner product of f of x with itself, just becomes 0 because there's no A0s in there, right? This one has an A0, and so you can take the derivative of this and you'll get something, right? This one doesn't have an A0, so this one's just going to go away. This one doesn't have an A0, so it's going to go away. So anything without an A0 goes away, just becomes 0. And everything with an A0, which is like this, this, and this, is going to come along for the ride, and we'll get a derivative of that. So keep that expression in mind, and I'm going to continue this right on the top of this page. And again, what we're looking at here is we're doing the derivative of that e squared function with respect to A0. And we will get this, minus 2 inner product of f of x with 1. Right, that was the first term. There used to be an A0 where the 1 was, but when you take the derivative with respect to A0, it becomes a 1. The second place we'll get a term is, so that first one was from this expression, right? This became a 1. The second place we'll get a 1 is right here, right? So A0 squared, that becomes 2A0. And so the next term we get is 2A0 inner product 1, 1. And then we get, this becomes a 1 right here, this A0. And let's see here. I feel like, did I copy something down wrong? I feel like there should be one more term. There should be an A0. I did copy this down wrong. There should be an A0 out in front of this term right here. I apologize for that. So there should be an A0 in the first 3 terms on the last line. And so this becomes a 2a squared, A0 squared. This one is just going to go away. And this one's also just going to go away. And we just get those 2 terms. So let's see here. The final part then is the sum of 1 with cosine nx. And then we also get the sum of 1 with sine nx. So there's 4 terms because there are 4 terms on the last page that had an A0, right? And it turns out 2 of them go away. So this cosine one goes away. When you do this infinite sum, it ends up just being 0 because it's an alternating series. So I don't remember what that means from Calc 2. And this one goes away because sine is odd. Right, so when you do this inner product, it's like the integral of an odd function, and so you're just adding up a bunch of zeros. But an alternating series means that you're doing like 1 minus 1 plus 1 minus 1 plus 1 or something like that, where you're just adding and subtracting the same thing over and over again, so it ends up just canceling out to 0. And so really, you just have that one expression. You want to set it equal to 0. And so you have minus 2 inner product f of x with 1 plus 2a0, 1 and 1. And you want to set that equal to 0. And solve for a0. Right, so subtract this one, divide by that, and you get a0 equals inner product of f of x with 1 and 1 with 1. Again, those are in inner products. They're not parentheses. I'm going to finish this off in just a second here, but I just want to pause and see if I can clarify something. Or if anyone has a question.
Real quick, at the beginning with the a squared over a0,
yep.
Are those D's or 2's?
It's a derivative thing.
Okay,
so it's a, I think it's technically a Greek letter delta.
Okay.
Sometimes people call it nabla. I'm not actually sure what letter that is. Let me look that up real quick. I guess nabla is technically the upside down thing. I think it's a Greek letter delta. But it means take the derivative.
Okay.
That's from calculus. Okay, and so let's go ahead and simplify this. So we can do those inner products, right? The inner product on both of these things, you integrate from minus pi to pi of what you get when you multiply the 2 functions. So we're going to multiply f of x and 1, and we're going to multiply 1 times 1. And we know how to do both those things. Well, we don't know how to do f of x, that stays alone, but this ends up being x from minus pi to pi, so you end up getting 2 pi. This one stays f of x, but in the bottom you get 2 pi. And this is exactly the a0 Fourier coefficient, right? So we can pull the 1 over 2 pi sort of out front. And this is a0 that we know. Right. This 1 over 2 pi integral of f of x is the a0 coefficient. So in other words, what we just found is that the Fourier coefficient that we've been using for a0 does actually minimize the error. And they're in the textbook if you want to look at them, but an and bn follow very, very similarly. It's just a little bit more complicated because there's more sums and things like that. There are more of those terms flying around. but it's actually very, very similar. And so you would do the exact same thing we just did, but at this step, you would take the derivative with respect to, instead of a0, like an. And so you'd be looking at like this term and this term, for example. And then bn, you'd be looking at this term and this term. But it follows very, very similarly. And when you do those things, you would end up deriving the actual Fourier series. I've always kind of gone back and forth about whether it'd be good to do this first or last. I'm following the textbook for one thing, and I think the textbook puts this kind of last because the last thing that we're going to do is talk about that error and minimizing the error and plotting the error, which is sort of its own topic. Like this follows a field of mathematics called numerical analysis. I know at least one or two of you guys are in that class this semester. I have no idea what you're doing in that class with Abdul, but what that class is supposed to be doing is talking about approximating solutions to functions and talking about like how we know when certain algorithms converge or not converge and how close they get to solutions and things like that. So anyway, this is an entire its own subject that if you're interested, you should think about taking more of. It's a very highly, involves a lot of computing, a lot of programming and things like that. I like that topic a lot. That was one of my, in grad school, you have to take usually, you have to pick like 2 subjects that you're going to specialize in. And my sort of main specialty is biological modeling, but my subspecialty is this numerical analysis stuff where we talk about error and things like that. So anyway, I'd love to talk to you more about that if you're interested. But this is just the final takeaway. If we want to minimize the error, we would want to use these coefficients, which we know as the Fourier coefficients. Nothing groundbreaking there, but just kind of showing you how we can get that using some simple calculus. Okay. Thoughts or questions before we move on? Just realizing I might be missing a page here. Let me see if I can find this blank page. I have this page, but I think there's a page 31 I'm missing. Give me 1 second while I look for that right quick. Okay. I think I actually have that right here. Okay, I'm gonna keep going here. Sorry, I just got a little confused there. I'm missing page 31, but I did find it, sort of, but I didn't find the maple part for it. Anyway, let's keep going. So this final page here, or almost final page, is just talking about a couple theorems related to these things. And so this first one is talking about, it's showing us the quantity E again, right? So this is the error again, which is the difference between the function and the approximation again. And it says it's going to be the minimum if and only if the coefficients are the Fourier coefficients. That's what we just showed. And moreover, the actual minimum value is given by this thing right here. So this is the closest you could possibly get to the actual difference between the function, the total difference between the function and the approximation given a specific m, right? And so it sort of measures how close Fn is to f. You can see it's using the Fourier coefficients. And this sort of leads directly to these two theorems down below here, which involves these terms. And we won't spend too much time with it here. Let me just sort of point out the differences here. So again, the terms a0, an, and bn, and the integral of s squared is in both of these expressions. And it's actually the same expression, except there's two differences. The main difference here is this is a partial sum, where this one here is an infinite sum. And this one has this value on the left, which has all the Fourier coefficients being less than or equal to the integral of the function on the interval. But the idea is that if you let n go to infinity so that this sum becomes infinite, the less than or equal to part becomes inequality. And this term on the right here, right, is a0, just to be clear, right? You're integrating the function of f of x squared from minus pi to pi. That's a0. And so the consequences sort of this is just kind of what it says down below, which is we know the first formula tells us sort of the value of the error. So if you're asked to calculate the error that actually exists, you can just use this formula. And for the second two, this is sort of the key thing, the key takeaway from this page is that if this integral on the right here, this integral of f squared is finite, in other words, if there's no discontinuities and things like that between minus pi and pi, you're going to get a finite integral. And so if you get a finite integral, then what this is saying is the sum will converge, right? So if this sum is always less than or equal to this, if you let n go to infinity and this is a finite thing, it runs into the finite value. If this is infinite and you let it go to infinity, it may not actually catch up to that. So this is just sort of saying, if this is a finite thing and you let this one go to infinity, you're going to get equality here. And the nice thing about that is if the sum ends up converging, this is sort of saying that, hey, after you plug in enough terms, i.e. infinitely many of them, you're going to approximate the function exactly. Well, that means that the error eventually goes to 0. And so you can approximate the function as close as you possibly want it, in other words, as long as you have a finite integral on the right. In terms of the homework, we use this expression in the homework to calculate the error between, or it can be used to determine the error of a particular Fourier series. And so the thing that just sort of tripped me up was I have stuff prepared for page 32. So we've actually seen the thing on page 32 before. The thing on page 31 is slightly different, and I don't have a maple code prepared. I don't think, at least. I'm just give me one more second. For some reason, it wasn't. That page slipped out of my packet here, so when I was trying to prepare for today, I just didn't see it. Maybe I don't have one. Maybe it's cosine series. Okay. So let's look at 31. Let me just say something about 30. Let me do page 32 first. And For this one, I'm going to switch over to Maple, and I'm going to say, I'll actually print out and attach some Maple output. But I'm going to switch over to the Maple code called Fourier Series 2. Actually, in the Dropbox, it's called Fourier Series A. So I'm going to switch over to that in a second here, but let me just read the problem. So we're talking about the square wave. As a quick reminder, the square wave was the one that looked like this. I didn't mean to do this. It like does that and it repeats it over and over again. That's the square wave. That was one of the first things, or maybe the first thing we approximated with the Fourier series. And we already looked at it at Maple, and when we looked at it in Maple, I said, oh, we'll use this part at the bottom later. And so now is the time. I'm just going to pull out the notes where we saw that. So back in the notes, this is the square wave that we had looked at. This is page 15 of chapter 5 notes. And this is the series we had got when we found it. And we got this series because it was an odd function, and so it only had a sign, right? So this is like a sign series. And so that's what's written right at the top of the page here. Just as a reminder, that's where that came from class that time. And so the question here is, graph the square wave and its 9th order approximate Fourier series on the same axis. And so when it says 9th order, this means n equals 9. So use 9 terms in the sum. And then we're gonna find the error for n equals 10, 50, 100, 500, etc. And so that's what I'm going to do. I'm going to switch over to Maple and show that right here. Again, it's something you should be at least somewhat familiar with because we have seen this before. But I'm now sharing my screen. Oh, that doesn't show up on mine. I am sharing my screen. There we go. No, that's not it. I'm sharing my screen. There we go. And again, this is the Fourier Series A document. And here is the Fourier series being listed. So here is the actual Fourier series being defined. And you see we get the thing at the top of the page. And then here is the function we're trying to approximate be defined. And we know it equals -1 or 1. And then what's going on down here is we're plotting the function, which is going to give you the square wave, and then different versions of the polynomial. So this is like this, right? F9 is the 9th order one. So this is the first question is F9. And so I'm just going to delete the other ones and see if we can do that real quick here. So that's just the 9th order approximation right there. You can see it follows the general sort of curve or whatever, the general shape, but it's obviously not very good. And if we go down to the bottom and we actually want, we want to calculate actual E star. So here I am defining E star, right? It's the difference between the Fourier series. This is, what page is this on? This is the thing that's listed at the top of page 30. All right, this is E star that's listed at the top of page 30. All right, so I'm just defining it in terms of n, and you can see the n just goes into the sum. And then what you can do down here is you can plug different values into n. And so the thing at the top of the page is just asking us to plug in 9 to start. If I just plug in 9 and I run this whole document, it gives you this value. It's hard, I don't know what that value is, and so here's how you make that value into a decimal. When you do eval f and then you put the number 4 in there, it's going to take equation 4 and it's going to evaluate it and make it into a decimal. And so in other words, the entire error on this graph right here, the first one that's being shown, is 0.25, which is decently large. And then it's asking us just to repeat it for n equals 10, 50, 100, 500, etc. And so you can plot those by doing this. And you can see that the more n's you have, the better it gets. Let me see if I can just zoom in right there real quick. If we zoom in right there, you can see that the bigger n gets, the closer approximation we have. And then you can actually measure the approximation down here by just plugging in those values, right? So we're going to plug in 10, 50, 100, 500 into this n. And so we're going to approximate those different errors. And so I'm just going to run it one more time. I'll run the whole thing again. And it puts them, makes this very complicated looking expression because like this is one of the fractions. Can you see this thing on the second line? This is one fraction. And so it's huge, right? And so instead of like looking at that huge fraction, you can just apply the decimal and look at the decimal instead. And you can see that basically the more terms you add, the smaller the error gets. To the point where if you did 500 terms, your error is less than 1%, which is really nice. And this is, I hope you can recognize this is very valuable and important because in certain applications, you need to have your approximation be very, very close. Like if this is an MP3 or something and we want to compress it, if we don't have a good approximation, it's going to come out sounding really crappy. But if we have a really good approximation, then when we uncompress it or decompress it, or whatever you call that, it's going to sound really good. And so the better approximations or the better application we get. Okay. Are there questions so far?
Yeah, so trying to figure out how to phrase it. So like when you're talking about like an MP3, so if you have like an approximation of it, so you can then compress that approximation, like so you wouldn't be able to normally do that with the actual MP3.
So the actual MP3 is a collection of like sound waves, excuse me. Not even just sound waves, like harmonics and all kinds of stuff. Like when you record music, there's like 10 different instruments, right, on top of each other. All these instruments have their own sound wave, and each one of those sound waves is composed of harmonics, is what they describe it as in the other video. So like a bunch of things combined to make certain sounds. And so when you add up all those things, it's very complicated, and it requires a lot of energy or memory, to store all that information. And so the compression is when you take all that information that's in a bunch of different sound waves and all these different things, and you represent it as a Fourier transform. And so it's not that the sound itself was a Fourier transform and then you make it a more simplified one. It was a really complicated bunch of waves and all this stuff, and you represented it as a function, basically. That's the compression.
Oh, okay, because now it's essentially a singular function instead of potentially tens or however many it was before.
Well, it wasn't even functions before. It was literally like the waves themselves being stored, right? Okay. Yeah, which is why, like a movie or something like that, if you tried to save a movie or whatever, you store movies on your computer, they're like gigabytes and stuff like that. They're really big because it's lots of stuff being stored. But when you compress it, it reduces all these millions of different things that have their own sort of memory space, and it compresses it into like a function, which is a lot less to store. Now, maybe it's a bunch of functions, or maybe you need 1 million terms in your function to make it a nice approximation, but it's still going to save you space compared to saving them all separately.
Okay, and so then when you unzip it, it just reverses it, or you're just using it as that compressed version?
I don't have experience with that, but my understanding is that what it would do is it would take this sort of function representation and it redraws the song or the picture or something like that you had compressed.
Okay.
And so it rebuilds up what you had, and then it'll take up that space again because all of a sudden it recreated all the stuff that it was trying to compress in the first place, right?
Okay.
Yeah. But again, I don't have a lot of hands-on. I don't have any hands-on experience with doing that without, other than just compressing stuff on my computer. Like I haven't coded things like that in math, in a math program to see it. I'm just kind of learning about it on the fly here. I think it'd be a cool project, though. I've always kind of wondered about if someone's interested in tackling a project like that. Maybe we could try to write some functions that would compress things, or like look under the hood of compression softwares or something like that. I'm just trying to look for the last thing here, which is on page 31. Again, it's just the same exact thing as page 32, except it's for the sawtooth wave. And so I'm just looking through the notes, trying to find the sawtooth wave. I don't remember which the sawtooth wave was. I don't think I labeled it as the sawtooth wave in the notes. Maybe it was when we were doing the even and odd periodic function thing. Just one moment. So the sawtooth wave, yeah, is that one. I think it's the one on page. Page 22, 23 actually. Is that right? Maybe we never did the sawtooth one. So currently I'm just trying to look for this in the notes. So this is the last thing I just want to look at today, which was this sawtooth one. I'm not seeing, I thought the sawtooth one was what's on page 23, but that doesn't have the solution. Does anyone see the solution for that thing in the notes anywhere? I thought it was the odd periodic extension, but that would be, yeah, maybe this, is it actually? Minus. So I think this is actually this one, if I'm not mistaken now. This kind of looks like a sawtooth, right? The thing that was, I guess, confusing me was that this one has been simplified with the -1 squared, and we know that cosine n pi turns into -1 to the n. So I think that's probably this one. And so is that the cosine series? If we open up the cosine series one in Dropbox, I believe it would look like this. Yeah, so not sure if we actually want to do this right now or not. Let's see here. So if we wanted to actually do this problem, we would do exactly what we just did with this code. Because we already have this code. This is in the Dropbox. We've already solved the Fourier series. It's this right here. And it looks a little different, but I think that's correct. Oh, I know why it looks a little bit different. That's why it's confusing me. This one is the where we started talking about on the interval -1 to 1. And the one in the notes is talking about from minus pi to pi. So that's why it looks a little bit different. That's why there's not pi's in the answer. But anyway, we could do the same thing on this one, just using this kind of idea. And so we could redefine E star. So I can do that right here. Copy E star over. We're going to define F. Is F already defined? F is already defined, except this is the Fourier series from the last one, and instead we want to use the Fourier series from this one. And so is that right? Yeah. And so we could just instead, maybe we could just plug this in. So what if we just called this F? I'm not sure that's going to work. Let's try it. And then we'll do this too. Does F have an X in it? It does have an X. So this is a slightly different expression. I'm not interested in doing this on the spot, I don't think. Fortunately. So this would be approximately the right approach, but then we need to plug values in. So I'm not going to do this right now. But the reason I wanted to at least show this, or at least show you the codes to use, is because if you start looking at the homework, you're going to want to use these codes for that. So like this is the homework that's due next Thursday. And specifically in number 5, where it's asking about the minimum of the norm or finding E star as a function of n, this is where you would want to edit or start with, use the Fourier series A1. In Maple. So you do basically what I was just trying to do a second ago, but I'm sorry, I'm not going to do it just sort of right on the fly here. You want to just edit it so that you need to change the fn to match the fn of this function. So, you know, parts A and B are like finding the Fourier series, but then in parts D, you're going to plug that into the norm here. And I am happy to, maybe we could look at that together. Part of me also doesn't want to get too far in this because I don't think people have started this yet. I haven't answered any questions about this homework from anyone. So that makes me think people haven't really looked at it yet, which is fine. But maybe just sometime next week after you've had a chance to look at it, maybe on Tuesday, for example, we could go back in and try to work on that a little bit together. Okay, I think I'm going to stop there. And I'll remind you again, this is the last page. This is the last thing in that section. And so I'd like to start chapter 6 on Tuesday. And so chapter 6 is in the Dropbox. If you could possibly print that by next week, that'd be great. It's about 20 pages. And I think that'll take us to the end of the semester. All right, I'm going to stop recording.